there's no in-class test. I thought I made it clear on the first day. But anyway. Now, last week we talked about bias and MSC. We did 6 examples. Now, what I'm going to do this week is what I'm going to do today is to do a couple of more examples on bias and MSC, and then I will move to a new topic, which is estimation, right? Which is maximum likelihood estimation, right? So this is example example 7. We did 6 examples last week. This is example 7. Right, so we have a random sample from a uniform distribution, theta to theta plus 1. X bar is a possible estimator of theta, and we want to find the bias and the MSC. So to define the bias, you see the definition of bias, I'm sure you know, is this, right? And this you can write as the expectation of and you should take the expectation inside. You get 1 over n times the sum of the expectation of xi minus theta. Now, I'm sure you know the expectation for a uniform random variable is, I gave you do you remember the formula for the mean or the expectation of a uniform? It's a plus b divided by 2, right? So in this case, theta plus 1 divided by 2 minus theta, right? So this is going to be 1 over n times theta plus a half times n. All right, so this is half. So the bias is equal to a half, so which implies that x bar implies that x bar is a biased estimator of theta. Okay? You guys with me? I'm doing many examples just to make sure that you follow the concept, right? Now, the next thing we want to work out is the MSC, right? So MSC of x bar using property 1. You remember property 1, which says that this is the same as the variance of x bar plus the bias I saw some of you writing variance minus. I don't know where you get that from. in the quizzes that I marked so far. Some of you write variance minus this. I really don't know why you saw. I mean, it's variance plus, guys. It's variance plus the square of the bias, okay? Okay. Now, if you take the variance, inside, you get 1 over n squared. Okay. Now, do you guys remember the variance of a uniform variable? We have uniform from theta to theta plus 1. All right, so it's b minus a squared divided by 12, which is theta plus 1 okay, so this will be okay. So this is the MSC for the estimator, and clearly as n goes to infinity, this approaches 1 over 4 as n goes to infinity. So what it means is that x bar is not okay. You follow me? Right, so remember, for estimator to be consistent, the MSC must approach 0, right? Okay, which is not the case here, right? Okay, that's example 7. The last example I will do today for bias and MSC is example 8. Right here we have two possible estimators. Two possible estimators of B. So the question is, which is better? You will get a question like this in the exam, which is better and why? Right? So I did a question similar to this last week. So what you need to do is to find the biases and find the MSCs for both estimators and compare them, right? Okay, so I will start by finding the biases of the two estimators, right? This is the definition of bias, so this becomes the expectation of now if you take the expectation inside, guys, you get half of 1 over m times the expectation of x plus 1 over n times the expectation of y minus p. I'm sure all of you know the formulas for the binomial random variable, right? So this is half 1 over m. It's m times p, 1 over n times n times p minus p. So if you simplify this, you get p minus p, which is 0. So the first estimator has bias equal to 0, right? Now let's see what happens. Let's see what happens for the second estimator. So I'm going to find the bias of the second estimator, which is this, right? So it's going to be the expectation of x plus y divided by m plus n minus p. Taking the expectation inside, you get expectation of x plus the expectation of y divided by m plus n minus p. Expectation of x, I'm sure all of you know, is mp plus np divided by m plus n. So this is p minus p, once again, is 0. So in terms of bias, so the conclusion is, well, the conclusion so far is the following, that because both estimators have bias equal to 0, which is a good thing, as you know, right? Okay, so both estimators are equally good in terms of bias, right? Now the next thing you need to do is to find the MSC, right? So let's start with the MSC for this, right? Which is now, we know that this guy is 0. We have already shown that it's 0. So this is simply the variance of half of now, when you take the variance inside, you need to all the constants need to be squared. I'm sure all of you know that. Yeah. Right, so what will happen? So this will become 1 over 4 plus 1 over m squared times the variance of x plus 1 over n squared times the variance of y. Okay? Now, the variance of x, I'm sure all of you know the formula. The formula for the variance of a binomial is m times p times 1 minus p. This is 1 over n squared times n times p times 1 minus p. You guys with me? Okay. So if you simplify this, then you get quarter times 1 over m plus 1 over n p times 1 minus p. Okay. So that's this is the variance, sorry, the MSC for the first estimator. Now let's do the same thing for the MSC for the second estimator. Once again, this is variance of P2 hat plus the bias. We know that this guy is 0. So this is variance of x plus y divided by m plus n. Okay? All right, taking the variance inside, this becomes 1 over m plus n squared. In brackets is variance of x, variance of y. Okay? So this is 1 divided by m plus n squared. Variance of x is m p 1 minus p. Y is n p 1 minus p. All right, simplifying, you get 1 divided by m plus n times p times 1 minus p. So this is the MSC for the second estimator. So let's summarize. So in summary, MSC of the first estimator is this, right? And the MSC of the second estimator is now the question is, remember, we prefer the estimator that has the smaller MSC. So which one of these is smaller, you think? Guys, think. Okay, because sometimes it's difficult to know. Sometimes it's difficult to know which is smaller without actually doing the calculations, right? So let's suppose, I'm just guessing. I mean, I don't know the correct answer. So suppose right? Suppose the second estimator has a small MSC. So that's the same as saying that okay. All right, so these two guys cancel, so this becomes yeah? You with me? Correct me if I'm wrong. It's quite possible I may be making a mistake. So this is 4m and So I should put an equal sign in case. So my guess is correct. So I have proved that the MSE of the second estimator is less than or equal to the MSE of the first estimator. So in terms of all right, guys. So any questions on this? Are you okay or not? Hello, guys. Yes? No? So, I mean, so I done two, this is the second, I mean, I did one question similar to this last week, and this is the second question I'm doing of this type. You are given like two or more estimators asked to compare them, right? And this is the kind of stuff you need to do, right? All right, now I'm going to move on to the next topic. So now, so far we talked about you guys okay? You know, so far we talked about estimators, how to compute the bias, and how to compute the MSC, right? But the question is, how do you actually come up with the estimators themselves? We haven't talked about it, right? I mean, how do we actually, I mean, all the estimators I talked about so far, I mean, how do you actually come up with them, right? And that's what I'm going to talk about today. A popular method for, there are a variety of methods for constructing estimators, but a popular one and the most widely used one is known as the method of maximum likelihood. So I'm going to talk about the method of maximum likelihood right now, okay? The method of maximum likelihood, right? So this is one of the most popular methods for constructing estimators, right? So suppose Okay. Suppose you have a random sample. Remember, the word random sample and IID are the same, right? I will use them interchangeably. Okay, so suppose you have a data from a continuous distribution with this PDF, where theta is an unknown parameter, and we want to estimate theta. So the you guys okay? Yeah. The ML estimator for the ML is short for maximum likelihood. The maximum likelihood estimator for theta can be obtained as follows. The first step the first step is to compute or calculate this, which is the product of the density function over the data points x1 to xn, right? And this is known as the likelihood function, right? The second step take the log of the likelihood, right? So if you take the log of the likelihood, it's a log of the product, which I mentioned earlier in the course, that the log of the product is the same as the sum of the logs. Okay? And the third step is to differentiate the log likelihood with respect to theta and set it equal to 0. So solve the equation that you take the derivative with respect to theta, set it to 0, and solve for theta. And step number 4, let me call this star. If here MLE stands for maximum likelihood estimator. If sorry, I need to squeeze this in. So if the second order derivative of the log likelihood at theta equal to theta hat is negative, then the solution of this equation star is a maximum likelihood estimator. All right? So it's a very simple procedure, guys. It's a very simple procedure. So the first step is to write down the likelihood function, which is the product of the PDF over the n data points. The second step is to take the log likelihood The third step is to solve the equation that you differentiate the log likelihood with respect to the parameter theta, and then you set it equal to 0, and so you solve that equation for theta. And the final step gives the answer that theta hat is an estimator, is a maximum likelihood estimator, or MLE, if the second order derivative of the log likelihood at theta equal to theta hat is negative, right? So that's for continuous data. Now, let me do the same thing for discrete data. Now, this here I have assumed that the data is from a continuous distribution. Now, suppose see, I mean, if you look at the top of the page, I don't know if you can see it, I've assumed that the observations are from a continuous distribution. Now, suppose the observations are from a discrete distribution with PMF. Remember, PMF is for a discrete, whereas PDF is for a continuous, right? Where so in this case, the procedure is pretty much the same. The only difference is that you'll be using, in place of the PDF, you'll be using the PMF. So the procedure, so the step one is to calculate L of theta, which is the likelihood function, and it will be the product I from 1 to n of the PMF, right? So this is once again known as the likelihood. This is known as the likelihood function of theta. Okay, that's step number one. Step number two is once again take the log of L of theta. Okay. And step number three is the same. So you solve the equation you solve this equation. Let me call this star once again. Okay, for theta. And step number four is the same once again. So if All right. Okay, guys, so the four-step procedure is precisely the same, except the only difference is that in place of the PDF, you have the PMF, all right? Now, let's try to do some examples, all right? So I will try to do as many examples as I can, right? So starting with the simple one, example 1. Right, so here we have a random sample from an exponential distribution with parameter theta. Obviously, we are assuming theta is unknown, and we want to find the estimator or the maximum likelihood estimator for theta, right? All right, the first step, because this is a continuous distribution, obviously exponential is a continuous, right? So now, do you guys remember the density of exponential? The PDF, I mean. The PDF of exponential is theta. If you don't remember, this is the PDF of exponential, right? Now, if you take the product, this is where you need, I mean, unless if you're not confident, you need to use the correct rules, all right? This is theta n. Okay? So this is the simplified form of this. So that's step 1. Step 2 is to take the log. So you should take the log of the likelihood, which is the log of this, which is n log theta minus theta times the sum of xi, okay? Okay, so this is the log likelihood. And step number 3 is to take the derivative with respect to theta. So okay, and set this to 0. Now, if you solve this equation, guys, what do you get? This gives you theta hat is equal to n divided by the sum of xi, which is 1 divided by the sample mean. And step number 4 is to take the second order derivative, right, which is the derivative of this term here, which is minus n over theta squared, which is negative, right? So we are done. So the conclusion is the following. Hence, are you guys with me or not? So this is a very, very simple procedure. Yeah. First step, write down the likelihood function. Second step, take the log. Third step, take the derivative with respect to theta, set it to 0, and solve for theta, right? And step number 4 is to make sure that the second order derivative is negative, which is the case here, right? All right, so the conclusion is that the maximum likelihood estimator for theta is 1 divided by the sample mean, right? So this is how this is one way of constructing estimators for parameters, right? All right, now let's look at the second example. Example 2, this is from a discrete distribution. Right, can you read this? It says, you have a random sample from a Poisson distribution with parameter theta, and we want to find the MLE of theta, right? So the first step is to write down the likelihood function. Now, do you guys remember the PMF of Poisson? You must have done in probability 1. Yeah, this one, right? Okay. Okay, now you should take the product of this. This is, once again, this is the step you had to be really careful about how to do the product of this, okay? Use the formulas that I gave you right at the beginning of the course. So this is okay. So this is the correct simplification, okay? So that's part 1. Part 2 is to take the log of this function, which is minus n theta, plus the log of that is and plus minus the log of this. Minus the log of this, because you have taken the log of a product, is going to become a sum of a log, right? So it will become okay, so this is the log. Step 3 is to take the derivative with respect to theta. So it becomes minus n. Derivative of log of theta is, I'm sure all of you know, okay? And you set this to 0 and solve for theta. So if you solve this for theta, you get theta hat equal to 1 over n times the sum of xi, which I'm sure all of you know is the sample mean, right? So theta hat is the sample mean. Now, maybe I could do it here. Okay, now step number 4 is to take the second order derivative, right, which is this, yeah. You can prove that this is, I mean, this is clearly negative, but we only need to prove that this is negative when theta is theta hat, right? In any case, I mean, because theta squared is positive, this is positive, this must be negative, right? Hence, okay. Are you guys okay? Any questions on this so far? Yes, no? Okay. Example 3. I will do more examples on Thursday, but all right. So here you have a random sample from a normal distribution with mean equal to theta, variance equal to 1. And we want to find the MLE of theta. Can I give you this as an exercise for you for Thursday? Right, so before you come on Thursday, can you do this, guys? And I'll go through it. Okay, guys, so as you all handed in your quiz 5, I will mark them this morning and I will send it to you as soon as I can. Okay? For quiz number 6, you can use the result of quiz 5, right? So I will post the solutions to quiz 5 later today, so make sure you look at it before you do quiz 6. Okay? Hello.
Is the one that you wrote for? Is that N
Normal.
no, I got N
Comma 1. Yeah, there are two parameters for normal. Theta is the mean. You're late. It's okay. Okay, yeah, that's fine. Yeah. Hello, how are you? 3? Yeah. I'll be at 3. Yeah, I'll be in my room. Yeah. Yeah. Hello. Theta is a parameter. When you estimate it using data,